All right, so we're going to take a look today at section 7.2. And this is where we start to look at the Laplace transforms, sort of going in the forward direction as well as going in the inverse direction or the reverse direction. Okay, we're also going to take a look at transforms of derivatives if we get a chance to do that today. All right, and so let's start with a little bit of what we know. All right, so what we know is that back in Calc 1, we learned that we could take a derivative of a function. And this one, relatively simple example, we take the derivative of x squared and we get 2x. And if we integrate the output of that, so if we integrate 2x, then we get back to our original function, right? And so the important structure here is that derivatives and integrals are what we call inverse functions. Inverse functions, all right? And so we know a bunch of other inverse functions. Like if you think back to, your very early math days, you might remember when you learned how to add and then you also learned how to subtract. You learned how to multiply and you learned how to divide. You learned how to square and square root, right? So there were a lot of functions that you learned or transforms that you learned, but then when you also figured out how to undo them, then really you had the whole package, okay? And so that's sort of the idea of today, is that what we think about from yesterday's lesson. So yesterday we learned that this fancy uppercase scripty L means a Laplace transform. And unlike function notation, we don't use parentheses, but we use curly braces. And so yesterday we did a derivation of the Laplace transform of 1. And we also saw it on the table. And it turns out that in both cases, both the formal definition and the table, the Laplace transform of 1 is 1 over S. Okay. And so what we're going to be thinking about today, sort of keep the same format here. All right, so what we're thinking about today is that we can have a Laplace symbol, but if we add a little exponent of -1, then we're really saying the inverse Laplace transform. And so the inverse would mean if I have 1 over S and I want to go backwards, where did that come from? In other words, what function did I take a Laplace transform of to end up with 1 over S? And that would be 1, okay? And so we have, again, this pair of inverse functions. All right. And I'm going to say this according to the structure of the table that we have from Paul's online notes, okay? So if you look at how we read the table, if you read the table and you look at the left column and then you look to the right column, then you're finding the Laplace transform. But what we're going to do today is we're going to sort of go backwards. We're going to start at the right-hand column and we're going to look at what's happening in the left-hand column. Okay, so yesterday we looked at the left-hand column and we said, okay, let's plug things in. Let's find out what's happening on the output side. And now we're saying this was the output. Where did it come from? Okay. And so the good news is that Paul's online notes, and I'm sure other resources, have a bunch of examples on how to sort of go in both directions on this table. And so if that was something that was still a little unclear for you from yesterday, I would encourage you to practice going in the forward direction. But also, as we're learning what we learned today, you want to practice going in the backwards direction as well. Okay. All right, so with that, let's go ahead and take a look at the first part of our lesson for today, which is called inverse transforms. All right, and so let's assume that we have two Laplace transforms. All right, and we use that capital or the uppercase letter to denote that. And so we have capital F of S and we have uppercase G of S. And it turns out that that idea of linearity, that we talked about yesterday, still holds true. All right, meaning that if we have a constant multiple and some addition, when we unpack it, we can do the constant multiplied by the inverse Laplace transform. We can add it to the second constant times the inverse Laplace of the second function. Okay. And it would be important to note here that A and B are considered constants. All right, A and B are constants. And so today, well, the first few problems will definitely be pretty procedural. All right, so if you have the Laplace transform table pulled up, that would actually be really beneficial. All right, and I am going to ask for some input just so we can kind of make sure we're reading the table correctly. I don't want to put you on the spot or anything, but I want to make sure we know how to read that table. Okay. All right, so for the first few, what I'm going to do is I'm going to write it out in terms of the linearity. So I'm going to bring the constants out to the front. I'm going to separate the terms. Okay, so like if we have a capital F of S and a capital G of S, I'm going to split those up into different terms. You don't have to do that when you are writing your own, but I think I just want to make sure we know that it's sort of a step-by-step kind of process. Okay. Also, I could not figure out how to get my equation editor to write the Laplace symbols. So this right here, all these sort of italicized capital L's are meant to be the Laplace symbol. Okay, these are I do all the notes in Google Docs, and the limitations, apparently Google Docs does not recognize symbols like the Laplace transform one. So we've sort of hit that point where it no longer works for us, but that's okay. All right, so what I mean by splitting these up is I'm going to have 1, 2, 3 functions that I'm going to be taking the inverse Laplace transform of. Okay, and so for the first one, I notice that it's 6 over S, which is equal to 6, the inverse Laplace transform of 1 over S. Okay, so all I did was bump that constant out to the front, just like we do when we integrate or we take a derivative, and then I left the rest of the function on the inside. I do want to point out that my S's often get confused with 5s, at least in my own brain. And so if that is something for you, know that a lot of these, I'll try and make it super clear, but if you also have that same problem, just figure out a way to make it super clear, okay? I think S was a very unfortunate letter to be chosen, but here we are. Okay, and so the second one would be negative the inverse Laplace transform of 1 over S minus 8. And then my third one will be plus 4 times the inverse Laplace of 1 over S minus 3. Okay. And so with this, if we could go ahead and look at the table, all right? And according to the table, let's try and maybe color code these a little bit. We're looking now at the right-hand column, all right? And where do we see 1 over S in the right-hand column? I believe that corresponds to number 1 on that Paul's online notes table of Laplace transform, right? So we see the 1 over S. So now we want to go to the left-hand column and see what's there. we can replace everything in the orange with a 1. Okay. Minus, let's pick a different color. All right. So according to the right-hand column in the Laplace transform table, find something that looks like 1 over s minus 8. Where did that come from? What was my f of t function that came from? And go ahead and type that into the chat. Yep, it's like number 2, exactly. And so what is our a value for this particular one in the blue? It's 8, right? It's 8. So what I'm going to replace this thing in the blue with is e to the 8t. So instead of at, I have 8t. Now it looks like the last one is actually going to be very similar, right? The inverse Laplace of 1 over s minus 3, that means a is 3. So I'm going to have 4, because I had that constant out in the front, 4 times e to the 3t. Okay. And that gives us a final answer if we want to just kind of clean that up, of 6 minus e to the 8t plus 4e to the 3t. Okay. So the first few examples are pretty straightforward. We just really want to make sure that we are reading the table correctly and that our numbers and our accuracy, that we're really practicing that part. Okay. And there's one small thing I want to point out about this example before we move on, which is I've seen some folks do this, not that many, but I've seen some folks do this. I think it's because we're sort of, our brain is on overload with so many other high level concepts. But I just want to clarify that e to the 8x or 8t plus e to the 3t, I can't combine those. Like that does not make e to the 11t. Okay. How could I change this part of the equation or the expression if I wanted to combine my powers? What would I need to change about what this looks like right here? And that might be a weird thing to think about if it's not a mistake you've ever made. But
it'd have to be like e to the t to the 8th plus e to the t to the 3rd.
yeah, like if that could be one way, but I think what I was looking for is if that addition changes to a multiplication.
Oh, okay.
Right? That's really when we're looking to combine those exponents. So I love that people know their exponent rules, like parts of it. Like I know I need to like add my exponents here, but we only do that when we multiply the terms together. Okay. And so that led, I think, some people into some very strange answers. But if you're getting some strange answers, maybe just go back and make sure you didn't make like a very simple mistake. And simple meaning I know that you know how to add exponents, okay, or when to use those. All right, so let's carry on. Recall that all of these capital L's are meant to be the Laplace symbol. All right, so whoever's writing that equation editor in Google Docs, if you ever want to update that, that would be super awesome. All right, what line in the table does this one come from? 1 over s squared plus 7. 1 over s squared plus 7. And it's okay to say I'm not sure yet, right? But let's look at that table and see if we can see potentially where it might come from. Or
Is
what is
it line number 7?
Yeah, it's pretty close to line number 7, right? So in line number 7, we have a over the quantity s squared plus a squared. Okay, I hate that it turns into a capital. There we go. All right, so a over s, not x, sorry, s squared plus a squared. And so in order to use this sort of rule, what we need to do is we need to make sure that our numerator here is actually the square root of that a squared term, right? And excuse me, as it stands right now, that's not the case. And so sometimes we'll find that we need to do a little bit of algebraic manipulation to make it in the form that we want, all right? And so here's what I mean by that. We're going to do the inverse Laplace. And I'm going to do this. I'm going to say, I'm going to multiply by 1, okay, in a very intentional way. I'm going to multiply by square root of 7 over square root of 7. Okay, so all I'm doing is saying 1 in a very fancy way. And a very clever way, in a way that will help me move forward in this problem. And the reason why this is helpful is because we know when we multiply fractions that we're really just multiplying across, right? And so I'm going to go ahead and I'm going to take this square root of 7 and I'm going to move it to the numerator over here. I'm going to multiply that numerator across. 1 over square root of 7 times square root of 7 over s squared plus square root of 7 squared. Okay. So now look what I've created. I've been able to match the expression now pretty much exactly to line number 7, right? I have a over s squared plus a squared. Okay. So now that I've matched the form, the beautiful part about this is 1 over square root of 7, that, my friends, is a constant, right? It's just like this 6 that I had over here. I can bump that out to the front because of that constant multiple property. And so what we really have here is 1 over root 7, the inverse Laplace of square root of 7 over s squared plus square root of 7 squared. Okay. And now we can use that table and we can say it's going to be 1 over square root of 7 times sine of square root of 7t. Okay. And so this would be the original function that we took the Laplace transform of to end up with 1 over s squared plus 7. All right. So let's get these 2 questions on one page for you. And let's see if there are any questions from you before we sort of continue on our merry way of example. All right. Well, if questions come up along the way, I trust you to ask. All right. You can always send a private chat if you're like not feeling like you want to ask it in front of the whole class. That is absolutely fine. All right. So let's take a look at these 2 examples right here. Okay. We're going to take a look at example 3. Again, this is our Laplace transform symbol. All right. And so this time I see that I have a linear combination of 3 different functions. And so I'm going to go ahead and bring all those constants out to the front, split it up into 3 different things. And while I'm doing that, if you could sort of start to look at the table and see if you can match up which line we're going to use for each of the 3 inverse Laplace transforms. All right. 19 inverse of 1 over s plus 2 minus inverse of 1 over 3s minus 5. Oh, there we go. 5 plus 7 inverse Laplace of 1 over s to the 5th. All right. So we've taken this problem, we've broken it down into 3 smaller problems, okay? And I think that each of them are sort of different in terms of matching things up. There's a small twist to each of these, okay? And so let's begin with this first one. I have 19, the inverse Laplace of 1 over s plus 2. And so maybe one thing I want to note is this looks a lot like line number 2. So I'm going to put a number 2 here just so we can kind of keep track of which line on the table we're referring to. But the small twist for this first one is that A is not 2, right? That is probably the most common wrong answer that I see. We want to be a little bit more clever, a little bit more attuned to detail here, so that we know that this A value here is actually -2, right? So 19 e to the -2t. All right, the second term, all right, the inverse Laplace of the second term, we're actually going to need to do a little bit of algebra again, okay? Note that this one probably looks the closest to line number 2. But the problem that we have is that the coefficient of s is not 1. And in our table, that coefficient's a 1. So we need to make this coefficient to be a 1, all right? And so let's do a little bit of that algebra here. We have the inverse Laplace. I'm going to go ahead and factor out a 1/3 from that fraction. So 1/3 factored out gives me 1 over s minus 5/3, right? Because if I take a 3 and multiply it into the s, I get 3s. And then 3 times -5/3 gives me -5. So sometimes we need to do a little bit of work. That might just mean taking a look at that sign and making sure we have the correct sign for our letter. Sometimes we actually need to factor something out to preserve the coefficient that we want, okay? And let's see, which line do you folks see matches most with that last term that we have here? Right, and I think this one is tricky. I think this one is tricky for sure.
This is going to be number 3.
Yeah, this is actually number 3 in disguise, okay? And so it's okay if you were like looking at the whole table and you're like, I don't even know, okay? But I think the indicator here is really that we have s to some power in the numerator, okay? Meaning that we have s to the 4 plus 1 in the denominator, all right? And when we have that, that should be our clue that we want to use that third line. But like before, we need to construct something that looks exactly like what we have on the table. In other words, we need to find n factorial divided by s to the power of n plus 1. And so we're going to multiply by a clever way of saying 1 again, okay? And what are your thoughts? What should I multiply by to make this into a closer to a form that I want? And I'll even write the 5 as 4 plus 1.
Is it 4 factorial?
Yeah, let's get that 4 factorial in there, right? If we want to match the table and the table says n factorial, let's multiply by 1 in the most clever way we can, right? So that we can begin to match things in the table. And so if we typewriter around, we get 19e to the negative 2t minus, let's see, 1/3 e to the 5/3 t, right? So that would be the inverse Laplace transform of the second term. This would be the inverse Laplace of the first term. And I'm going to go ahead and do a couple things at the same time. I'm going to keep the 7 out here, but I'm going to bring that 4 factorial in the denominator to be underneath that 7 in the front. Okay, so plus 7 over 4 factorial. So I brought those constants out to the front, but I'm going to keep this 4 factorial in the numerator inside there, because then I have 4 factorial over s to the 4 plus 1. And so using our table, that tells us that we should end up with t to the 4th power. This is our third one. This is our do a little bit of algebra part. And this is where it originally came from. Okay. So it's not too far different conceptually from the idea of like U substitution or chain rule, that when we're shifting some things around, we need to compensate for it, especially if it doesn't already look like the form exactly that we want. Okay. All right. So that's our example 3. Any questions before we move on to example 4? Well, let's keep moving forward then. All right, so what we have here, right? So we have this Laplace transform. And I think this one, let's kind of look at our table for a moment before we start thinking about how like we might use algebra to our benefit here. So in looking at this, are there any lines that you feel called to in the table? And if so, which ones and why? What lines might be calling to us from the table? And it's okay if you're not sure.
I think 7 or 8, probably.
Yeah, it looks most like 7 or 8, right? And I really like that. I don't know if this was actually your strategy, but I think sometimes focusing on that denominator is actually really helpful in finding some structure there, right? We noticed that in example 3, even though 1 over s to the 5th didn't really look like anything from the table necessarily, that denominator s to the 5th actually gave us a clue which line we were looking at, okay? And so here's what we're gonna do, all right? We're gonna use a little very useful algebraic trick that maybe you might remember from your very first days in working with fractions. But let's say that I had 1/3 plus x over 3. How else could I write that? Right? How else could we write 1/3 plus x over 3? Yeah, we could just add our numerators and keep the denominator and call it a day, right? We're so used to going in this direction that sometimes we forget that if we started with 1 plus x over 3, we could say that is the same as 1/3 plus x over 3, right? In other words, we could take one fraction and turn it into multiple fractions. And that's exactly the idea we're going to use here for our Laplace transform. All right, so we're going to see that we have the Laplace inverse transform of -2s over s squared plus 4. All right, that's going to be my first fraction, plus the inverse transform of 6 over s squared plus 4. Okay, so we're taking this idea of I have one fraction, but if I could match one of those to the one on line 7 and one that's on the line 8, then that would actually help me move forward in terms of solving this problem. Okay, so let's go ahead and bring those constants out to the front. I'd like to bring the constants out to the front first. Not everyone does. Some people prefer to sort of keep it in there as they're working, and that's absolutely fine as well. But I'm left with s over, I'm going to write this as s squared plus 2 squared. Okay, 2 squared because if I know I'm going for s squared plus a squared, it's more helpful to know my a than it is to know my a squared. Plus the inverse Laplace of, whoops, let me go ahead and bring that 6 out to the front, right? So 6 times the inverse Laplace of 1 over s squared plus 2 squared. Okay. Now, if we take a look at this first function that we're looking at the inverse Laplace transform of, that matches exactly with the table. In fact, this matches exactly with line number 8. All right, so this one is line number 8 exactly. And so I could say that this is -2 cosine of 2t, right, just from the table. However, my second inverse Laplace transform is still not a total match for the table. What do I need to do to help me match that table exactly? In other words, what am I missing from this that would be really helpful so that I could use that table?
You need a 2 in the numerator.
I needed a 2 in the numerator, exactly. And so we're going to use that good old trick, multiply by 1 in the most clever way possible. Right? I'm going to keep this 2 in here, the numerator 2, so that I can match my table, but my denominator 2, I'm going to go ahead and divide out to that so that it'll be with the 6. Okay. So I get -2 cosine 2t plus, whoops, 3 sine of 2t. All right. All right. So these first 4 examples, I would say, are some pretty fundamental, they highlight a lot of fundamental algebraic tricks that are helpful for us. Let me go ahead and put a number 7 in here. And the next 2 examples that we're going to take a look at actually are going to be that moment where when I said we're going to need partial fraction decomposition, this is where it's going to start to come back up, okay? So for the next two examples, for example 5, you'll see that we have a lot more space because we're looking to do a little bit of partial fraction decomposition. And with number 6 as well, we're looking to do a little bit of partial fraction decomposition, okay? We'll get into some juicier ones as well with examples 7 and 8 that are all going to highlight some different strategies we might need to remember when we're doing partial fraction decomposition, okay? So let's take a look at example 5 here, all right? So one thing that might be really tempting to do, okay, I'm going to write this in red, not because it's like so horribly wrong, but based off of example 4, it would be completely reasonable for you to think maybe you need to do this, right? Split into 2 fractions. That's what we just talked about, right? So why wouldn't you use the skill that we just talked about, okay? But the thing that makes 5 different from 4 is indeed this denominator, right? Before, in number 4, I had s squared plus a squared, and that is exactly what I have on the table, s squared plus a squared. But here, in number 5, I have a quadratic, but it has a linear term. Right? It's not just s squared plus a constant. There's a linear term as well. And when I look on the table, I don't see any quadratic denominators with a linear term, okay? And so what we're going to use here is instead of splitting them, we're going to factor that denominator and see if we can rewrite this using partial fraction decomposition, okay? And so let's try that out. We have the inverse Laplace of s plus 7 over, when I factor the denominator, we end up with s minus 5 times s plus 2. Okay, so we're going to use a different strategy here because our old strategy did not match anything exactly on the table. Okay. And so if we could write this as the inverse Laplace of something over s minus 5 plus something else over s plus 2, now we see that we might be able to match line number 2 in the Laplace transform table, right? If we could do this, we could use line number 2, and that would make our life a lot easier. And so to get to that point, to find our A and B, this is where we're going to bring back that partial fraction decomposition, okay? And so if I take my initial s minus 5, s plus 2 equals A over s minus 5 plus B over s minus 2. And I'm going to create a little bit of space here on both sides so I can think about what I need to multiply each one by, right? And I realize I need to multiply the first fraction by s plus 2 over s plus 2. And I realize I need to multiply the second fraction by s minus 5 times s minus 5, right? This gives me the same denominator on both sides, so I can get rid of that denominator and only focus on the numerator. This will give me s plus 7 equals A times s plus 2 plus B times s minus 5. Now, for these cases, you can set up a matrix, you can set up a system of equations, but one of the skills that we highlighted a few weeks ago was that we could also choose very clever numbers, right? And that tends to work out a lot better when we have linear factors. And so I'm going to choose s equals -2. I'm going to see what happens with that. And I'm also going to choose s equals 5. And the reason I'm choosing those numbers is s equals -2 is going to zero out this first term, so I can find b. And the reason I'm choosing s equals 5 is because that will zero out the second term and I can solve for a. Okay. I just have to remember to plug in -2 everywhere I see an s, and then I need to plug in 5 everywhere I see an s, like on both sides. Okay. So if I plug in -2 on the left-hand side, I will get 5 equals, let's see, 0 plus b times -7. All right, so we're going to get b equals to -5/7. And then I'm going to repeat the process with 5, plugging in everywhere. So 5 plus 7, that gives me 12, which equals a times 7 plus the second term zeros out. And so I get a to be 12/7. Okay. So my suggestion to you is if you have linear terms that are not repeated, I would definitely just choose a clever number and plug it in. Okay, you can, of course, do this however you want. There's a multitude of methods. Just make sure you demonstrate or you explain to me which method you're using. Okay. But all of this is to say we can go back to this problem and now we have an A and we have a B. And so now we can split this into 2 inverse Laplace with coefficients and then just use our table line number 2. Okay. So let's go ahead and go back up here. We are going to have, I'm going to go ahead and bump the A out to the front. So I have 12/7, the inverse Laplace of 1/s minus 5. That's the first term. My B value was -5/7, so -5/7, the inverse Laplace of 1/s minus -2. Okay. I know a fair number of you don't need to take this step to write it as s minus a negative. Like, you know that s plus something is s minus a negative. But if you find yourself making those mistakes and you have a way to prevent yourself from making those mistakes, there's no shame, there's no judgment, right? I think sometimes we feel nervous about writing down more than maybe other people are writing down. We feel judged, or maybe we're judging ourselves around that. But if it's a technique that works for you, I would say go for it. Okay. But I think we can see more clearly now. We have a number 2 from the table, line number 2 from the table. And if we make sure that we are accurate with our A values, we should get 12/7 e to the 5t minus 5/7 e to the -2t. Okay. All right, so there is example 5 all on one page for you. All right, we sort of, if we were to mark off our process, we sort of started here. We then said partial fraction decomposition might be a really good thing to do. We stepped away from it. We did the partial fraction decomposition. Then we put it back in to our inverse Laplace transform. And finally, we used our table to match what we have in that line 4. Okay, so it's not quite linear. It's like 1, 2, take a side step to do some more algebra, and then use the table to finish things off. All right. All right. Before we move on to the next question, are there any questions that are coming up for folks who are here right now about partial fraction decomposition? Okay. So if there are no questions right now, let's go ahead and try our hand at another example. Okay, so we're going to take a look at example number 6. And upon looking at number 6, one thing that I am immediately sort of drawn to is this idea that my denominator is not just s squared plus a squared. It's a lot more complicated than that. And so what might be really beneficial is for us to think about using partial fraction decomposition, okay? It's not mathematically wrong to break this up into 1, 2, 3 fractions, but I don't know that that will help us move forward in a way that is efficient in solving the problem. Okay, so there's a difference between like a correct, something that's mathematically correct versus something that helps you move forward in a direction that you want to go in, right? And so looking at this and sort of all that internal dialogue, I've said, okay, I'm going to do the Laplace transform of, if I could have a over s minus 1 plus and b over, let's say, s minus 2 plus c over s plus 4, okay? Now let me take a moment to just kind of explain where those came from, right? So the s minus 1 part I think is pretty obvious, but where did the s minus 2 and the s plus 4 come from? Well, I just factored that quadratic that we have down there. Okay, so if you've been sitting there saying, well, but Judy, I know how to use the quadratic formula, why is that not good enough? Here we are. Okay, the quadratic formula will just take much longer. It is not a very finessed way of approaching the situation. When you don't want to find the zeros, you just want to factor, right? And the reason we want to factor is so that we can find the 3 partial fractions that add together to make the fraction that we have. All right, so we've got all of this as sort of our first step here, right? We've decided that these are the partial fractions that we want to find. And so maybe our step number 2 is thinking about actually finding values for A, B, and C, all right? This one's a little bit longer than the other one. There's just more terms, all right? So I'm gonna be really careful about my writing. S squared plus 6s plus 9 over s minus 1 times s minus 2 times s plus 4. And I'm going to build very carefully. Okay, so the first thing I want to multiply is a over s minus 1. And I notice that this has an s minus 1 like the denominator on the other side. However, it does not have s minus 2 times s plus 4. So that is something that I need to multiply there. Right. I'm going to do the same sort of idea with B. I notice that B has an s minus 2, but it is missing, whoops, it is missing s minus 1 times s plus 4. Finally, the last one, C, I'm also going to need to multiply. C has the s plus 4, but it is missing the s minus 1 and the s minus 2. Right. I'm pretty sure we're beyond this phase, but please don't take the time to multiply all of that out, right, in the denominator. That's not beneficial to us because we don't need, once we've matched the denominators on both sides, we don't actually need to worry about that denominator. We just need to worry about the numerators. And so let's see what we have left. We have s squared plus 6s plus 9 equals a. I'm also not going to multiply out s minus 2 and s plus 4. Okay. Now, while I'm writing this, what are some clever numbers that I can choose to help me find values of a, b, and c without setting up a system of equations. Yep, I would agree. Part of the reason we don't multiply out these factors is because each of those factors actually tells us which clever numbers we should choose. So we should choose S as 1 because that'll zero out some of the terms. We should choose S as 2 because that'll zero out some of the other terms. And we should choose S as -4 because that'll zero out some of the other terms. Okay. And so let's do that. Let's take S is 1. All right. S is 2. And S equals -4. All right. And I'll give you a moment to kind of work through that. All right, see what you get for A, B, and C. They are all fractions. So if you get a whole number, something went wrong. Okay, so all three of these values are fractions, which is another benefit to not doing a system of equations. But see what you can get for A, B, and C. I'm going to run to the restroom real quickly and I will be right back. Okay. All right, as you're working, I'm going to start to fill in the values here. Okay, so let's just make sure all of our computations are accurate, mine included. All right, good. It looks like our values are lining up so far. All right, well, at least two of us are in agreement. So I hope the rest of us are also in agreement about the three values of our coefficients, okay? Now, all we need to do, yay! Now all we need to do, we're gonna take our A, our B, our C, we're gonna stick them back into our partial fraction decomposition. And now we're gonna be able to use that table. We just have a constant that we need to multiply what we get from our table. All right. So, oops, I did not leave myself enough room. Let's go ahead and take this and not move it. No, shrink it. That is the other thing about using the tablet is I can shrink things if I run out of room, which when I'm writing on the board is a lot harder to do. But all right, so last but not least step, I'm going to go ahead and write this out. So I have -16/5, the inverse Laplace of 1 over s minus 1. Plus 25/6, the inverse Laplace of, wow, 1 over s minus 2, plus 1/30th, the inverse Laplace of 1 over s plus 4. And I know that last one is one that I need to be really careful about because that's not an s minus 4, it's an s minus negative 4. Okay. All right, last step, we're going to use that table, see what we get. Some of you are probably already there, so thank you for your patience, but we've got negative 16 over 5 e to the t plus 25 over 6 e to the 2t plus 1 over 30 e to the negative 4t. All right, oops. So there we go with number 6, a little bit of partial fractions takes us to a place where we can now use the table. All right, so we'll add that to that list of skills that is helpful. All right. I think we have a couple more examples here, which actually might be a really good breaking point for us to finish with these last 2 examples here, okay? So we're gonna show a few small twists on how we set up our partial fraction decomposition, all right? So everything that we've seen so far has been linear factors on the bottom. In other words, if we look back up here, we have a whole bunch of linear factors, okay? And I would say that the general sentiment of setting up partial fractions is if you have a linear function in the denominator, you drop a degree, you get constants in the numerator. Okay. That also means that if we sort of continue on with this pattern, a numerator that is quadratic in nature would have linear numerators. Okay. So let's kind of see how that might look. All right, we're going to do 2 cases that I think highlight some special ways of setting up partial fractions. All right, so here is our first example of a special way of setting up partial fractions. Okay. So we have the inverse Laplace of, I don't want to write it there. We have the inverse Laplace of, I'm going to say a over s minus 6, right? S minus 6 is the first factor that I have in that denominator. And s minus 6 is linear. So I'm going to put a constant on the top. I'm going to put an a. Now, the second part, you do want to ask yourself a very important question. S squared plus 11, that is quadratic, right? We know that S squared plus 11 is quadratic. Is it reducible? Meaning, can we reduce this quadratic into 2 linear factors? And one of our answers might be, well, yes, it's reducible, but then we would get some imaginary numbers, okay? And so we're working mostly in the consideration of real numbers right now, okay? And so for that reason, we're gonna say that s squared plus 11 is irreducible over the real numbers. Okay, it's irreducible over the real number. Now, since it's irreducible, that gives us our s squared plus 11 as the denominator for the second partial fraction. Okay. Now, remember what I said earlier. this is an a up here, a constant, because the denominator is linear, and the linear 1 degree less is a constant. Well, if I have a quadratic here, 1 degree less would be linear. So I would write BS plus C. Okay, so I don't want just a linear term. I want like linear and constant. Right. I'm making such a big deal of this because if this setup is wrong, then the rest of your work is wrong. Right? If you set this up incorrectly, then you'll end up with an answer that is just very, very different than what it's supposed to be. Okay, so double checking this step, making sure that that setup is good, 9 times out of 10 will get you to the right answer. Right. But now that we have our setup, right? So let's see, we're using orange. Now that we have our setup, let's go ahead and take a look at that partial fraction decomposition. So we're going to have 2 minus 5s over s minus 6 times s squared plus 11 equals, all right, what am I going to need to multiply the first one by? Plus, what am I going to need to multiply the second one by? Well, the first one, I'm going to need to multiply by s squared plus 11. And the second one, I'll need to multiply by s minus 6. All right. Now, here's another place where I think sometimes things start to go wrong. We want to make sure we have parentheses in all the appropriate places, right? So that's why I've included parentheses around these terms, because it isn't just like s squared plus 11a. It's like the quantity s squared plus 11 times a. I would probably also need parentheses here around the bs plus c. But now that I've mashed all of my denominators, goodbye, I can get rid of them. And now I can focus on my numerators. So 2 minus 5s equals a times s squared plus 11 plus bs plus c times s minus 6. Okay. So if you were to choose some clever numbers that I could plug in and find a different number or find one of the constants, what would those clever numbers be? What would you want to choose?
Definitely 6. And then would you use negative square root of 11 or no? That would be too complicated.
Yeah, I'm so glad you said that, right? So remember, we're looking to find values over the real numbers. And so in this case, we can start to see a limitation to the process we've used before. And in particular, that limitation is we can use 6, that will get rid of this second term, and we can find a. But it's not going to help us find b or c, right? Because there's no real number that we can plug in for s squared plus 11 to make that 0. So here's my word of advice on this front. And you can try different methods and kind of see what shakes out. But I like to go ahead and find whatever constants I can find using this shortcut. So I will go ahead and find what happens when s equals 6. What do I get for a? Okay, so let's do that first, and then let's talk through some strategies on how to find the rest of them. So if I plug in s equals 6, I get 2 minus 30 equals a times 36 plus 11 plus the whole second part zeroes out. And so I'll get negative 28 equals 47a, and I'll get a equals negative 28 over 47. Okay. So as soon as I can find a value, then I want to go ahead and find it. That's how I like to approach it. But if you're really into matrices or systems of equations, that will also could be a viable option. Okay. All right. But if that's as far as it can take me, then what I'm going to do is I'm going to go ahead and expand out the rest of this and set up for whether if I were to use a matrix or system of equations. And so I'm going to be really careful about my distributions, about my foiling in this second term, right? And I'm going to get as squared plus 11a plus bs squared, see, minus 6bs plus cs minus 6c. Okay. And if I were to be setting up a system of equations, okay, what I could say is that all of the terms with the squared are going to create one system of equations. All of the terms that have just s are going to create another one, and then all of the ones just with the constants will create a third. And all of those correspond to whatever we have on the other side of that equal sign. And so since I already have a, it might be really nice to notice there's no quadratic terms on that left-hand side. So 0 equals a plus b. And since I have a, this makes it really easy to find b. B is just going to be 28 over 47. All right, so I found A, I found B. Now I just have to find C. I'm going to be really clever about what I'm choosing here. And I'm going to say that 2, which is a constant, equals 11A minus 6C. Okay, so 2 equals 11A minus 6C. And everywhere I see an A, I'm going to go ahead and put in my negative 28 over 47. So 2 equals 11 times negative 28 over 47 minus 6C. I'll trust you to do the work over here, but we get C equals negative 67 over 47. Again, if you want to go ahead and simplify all of this from the get-go, set up a matrix from there, that's absolutely fine. You don't have to do this first step if you feel like that doesn't really help you move forward in that problem, okay? But one thing you'll notice, and this is not always true, but often true, is that all of the constants we found have that same denominator, 47. So I'm going to go ahead and actually pull a 1 over 47 out of the entire inverse Laplace transform. Okay. And so that's going to give me, in this third step, I'm going to end up with 1 over 47, the inverse Laplace of, let's see, negative 28 over s minus 6. That was my first one. Okay, so this was my a over s minus 6. There it is. Plus, here's what I'm going to do to the second one, okay? I notice that I can actually split this one into 2 separate fractions. BS over that denominator plus C over that denominator. That's going to make it easier for me to view the table and find a matching component. So I'm going to go ahead and split that. I'll get plus 28s over s squared plus 11 minus 67 over s squared plus 11. Okay. I'm going to have to compensate, right? This first one, I pull out that negative 28, that's going to be just fine. However, For the second term and the third term, I'm going to need to multiply by some fancy way of saying 1 so that I can make sure it matches. And actually, for the second one, I don't need to, but it's for the third one. What do I need to multiply that third one by to make it match something from the table?
Square root of 11.
Yeah, we're gonna need to multiply by the square root of 11. Okay, so let's kind of just get used to the fact that we're gonna have some weird square roots in here that aren't perfect squares, and that's gonna be okay. All right, so the inverse Laplace of the first one, we get negative 28e to the 6t. That's straightforward enough from our table. For the second one, I'm gonna get 28. Let's see, s over s squared plus 11 is gonna be the cosine one. So cosine square root of 11t. And then the last one, I know I need to multiply by that square root of 11 over square root of 11. So I'm gonna get 67 over square root of 11, not cosine, sine of square root 11t. Okay. And so let's get that all on one page right there for you. All right. So sort of a throwback to, lots of matrices and systems work, but really the key to this is that first step. Did you set up your partial fractions correctly? Okay. All right, based on the time, let's go ahead and focus mostly on the setup for number 8. All right, I think that'll be a good place to finish off today. All right. So we have a system of equations here that actually has not a system, we have a typo in our function. This should be to the power of 3. So I'm going to ask you to change that in your notes. 25 over s cubed times s squared plus 4s plus 5. Okay. And if we start to think about what that partial fraction decomposition looks like, all right, here's another trick. All right, here's another trick. You see how this s happens 3 times, right? S times s times s. When we set up our partial fractions, we actually have to set them up to compensate for all 3 possibilities. Meaning we could have a over s, like maybe the denominator is just s. Or we could have b over s squared, like maybe there's 2 of those. Or we could have all 3 of those. Okay. I want to pause here for a moment because this is a place where a lot of students get confused, and rightfully so. Earlier, I said that if you have a linear denominator, that your numerator is a constant. But I also said if you have a quadratic denominator, you have a linear numerator. And I didn't follow that here. Here's why. Okay. We said earlier that s squared plus 11 is irreducible over the real numbers. It's not just that the bottom is quadratic, so the top is linear. We have to be more specific than that. If we have an irreducible quadratic factor, then we put the linear one on top. However, if it's reducible, like s squared is reducible to s times s, it's still 1 degree less than the simplest form of that denominator. In other words, 1 degree less than linear. 1 degree less than linear. Okay, so that's why that setup piece is so important. If you only have, if you start to have like a bx plus c and then a dx squared plus ex plus f, you're going to be sitting there looking at your question like, why is this so long, right? And some of them are long, but that would be maybe not in a productive way, okay? Now we do notice that we have a quadratic factor down here, s squared plus 4s plus 5. Is that reducible or not? All right, so that's where we have to be careful. S squared plus 4s plus 5. If it's irreducible, then I'm going to have a linear factor on top. But if it's reducible, I'm only going to have a constant on top. Right? So this is why factoring is so important. The numbers in this case do not work out to be factorable over the real numbers. And so we end up with s squared plus 4s plus 5. And our numerators, we just keep using letters, we get dx plus e. All right. This is a good place to practice and make sure you've really got the concept on how to set things up, right? Because if this is not correct, then all the other stuff is also not going to be correct, right? Now, I will tell you what the constants are, right? Because there's a lot more to this problem than the algebra that goes into finding the constants. But I think based off of where we are right now, this might actually be a good place for you today on your own time in the privacy of your own learning environment to go ahead and make sure that you can solve and confirm these constant values. Okay. And so we're going to go ahead and say, as our last line for today, that I'm going to go ahead and factor out a 1/5. Okay, because most of mine have a denominator of 5, I can also factor out 1/5 here and just make those numbers a little bit bigger. Okay, but it'll avoid me having more fractions inside of my Laplace transform. This will leave me with 11 over s plus negative 20 over s squared plus 25 over s cubed minus 11 s plus 24 over s squared plus 4s plus 5. Okay. And so what I'd like you to do today is this. Number one, make sure that you can confirm those constants. Find a method that works for you, matrix, system of equations, whatever it is, but find that value, find those values. The second thing I'd like you to start to look at is how do we find, like, which lines in the table do these 4 terms correspond to? Okay. And see how far you can get. But when we come back together tomorrow, we'll finish this problem before we move into the second half of 7.2. Okay, so do a little bit of pre-thinking, make sure that you can figure out those constant values, and then see how far you can get using the table to find the inverse Laplace transform. All right, and so we'll finish with that today. I'm going to go ahead and stop the recording.